Welcome, everybody, to today's CDAC webinar. It's a pleasure to introduce today's speaker, Professor Terrell McQueen from Johns Hopkins University. Terrell is a solid-state chemist interested in the design and synthesis of new materials, and in particular, he focuses on quantum materials, including quantum magnetism, superconductivity, heat, and light-induced charge separation through strong electron correlation. He's also worked on high pressure properties of some of these materials, and his most highly cited paper is on the iron selenide superconductor under pressure. In recent years, Terrell has turned his attention to AI ML approaches to materials discovery and design, which he'll tell us about today. He received his bachelor's degree from Harvey Mudd and his master's and PhD from Princeton, where he worked with Bob Kava. After a postdoc at MIT, he joined Johns Hopkins University in the departments of chemistry and in physics and astronomy. And he rose through the ranks there to become professor. He also has an appointment in material science and engineering. And for the past several years, he's led the bulk crystal growth facility of the NSF-funded Paradigm Center, which is in its 10th year and looks like it will continue for a while. Terrell, it's been some time from hearing from you. We've been looking forward for a talk from you for some time. So thank you for finding the time to join us. Welcome.
No, my pleasure, and thank you all for joining in this remote Zoom format. And thank you, Russ, and everyone else part of CDAC for the invitation. It's my pleasure to be here. Before I go, too much further, first of all, please unmute yourself and speak up if you have a question. I like things to be interactive. The second is, what I'm going to show you is the results of hard work of a very large team of individuals, including, members of my group. This includes both current and former graduate students and postdocs. I'll call them out individually when I talk about some of their work, as well as a whole bunch of undergraduate students, a whole bunch of whether in their first year or through research experiences, as well as full-time staff here at Hopkins, whether it's Satya and David, who are experts in crystal growth and data-enabled science, or Syed Kupaya, who was for our Institute for Quantum Matter, sort of the catalyst for the crystal growth capabilities there. And of course, all the funding that makes this possible, especially in sort of the current environment. So I'm going to go real quick through a background that I think most of you know. And then I would like to talk about AI-driven materials discovery. And I'm going to use superconductivity as the property with which to frame a discussion about some of those things. I will then express some of my considerations and opinions on that, and then talk about where I think the real problems lie in this whole space. So, as you all know, materials underlie lots of things. Materials, in fact, are so important in the world that we define the eras of human history after them, right? From the Stone Age to the Bronze Age to the Iron Age, and others would argue that we're currently in the Silicon Age. And as Russ alluded to, really the focus of my research is addressing this question, which is, what comes next? What comes after the Silicon Age? And one possibility is an age where materials take advantage of macroscopic quantum phenomena, in order to generate new and better properties. And so the idea behind a quantum material is in some sense very simple. When we go down to the level of atoms, we have very simple interactions. Electrons repel each other, but they are attracted to nuclei. Those are competing energy terms. And yet, as soon as you then put a whole bunch of nuclei with single electrons on them in a chain, all sorts of complexity can emerge, right? You can get the famous Peros distortion, which is a dimerization if you think of it like a chemist. But you can get other states too, right? You can have electron-electron repulsion that's so strong that it forces the electrons to become an insulator and stay on individual sites and become magnetic. You can have the inverse, what we in chemistry you might call charge disproportionation, where you get two, essentially 2020. And you can get other more exotic states such as this bond order wave. And so really, and of course the canonical example of this kind of phenomenology is the superconductor, shown here with with a magnet sort of levitating above a piece of superconductor. It's really a question of where are the electrons and how do they interact? And that, at the end of the day, is a chemical bonding problem. And so you'll see me switch between some more physicsy language and some more chemistry language for various parts of this that sort of reflects that duality. Okay. So there are a number of reports over the last 5 years that talk a little bit more in detail about what quantum materials are. If you're interested, there's a whole slew of them. You can go read a couple of these reports. A couple of them are shown here if you're interested. I think one of the testaments to how far this broad area of science has come, though, is data like this shown here on the bottom right, where the top is experiment, the bottom is theory. If the experiment didn't have that little bits of noise, you wouldn't really know which was which. And I think that's really impressive that we've gotten to the point where we can really start to predict things with reasonably high fidelity. And so this leads to a whole series of questions, which are the actual motivating questions for the research in my group. What are the different classes of these emergent electronic states that can occur? How do they arise from the pattern of atoms? That's going to become very important in just a minute when we talk about superconductors. And then what impact do these have on the various physical properties of interest? And does this then lead to new and useful technologies, right? So we spend a lot of energy in society trying to make things perfect, crystallographically perfect, and get rid of defects. Well, if you can make materials that don't care about the defects, then you don't have to do that, right? So there's lots of reasons to explore, how do you actually harness things that you might call defects actually in a very useful way? And does this lead to new kinds of computing, new kinds of sensing? At the end of the day, my expertise is really in the making of materials and in materials design. In other words, what materials to make. And, and that's sort of captured by this synthesis layer in this diagram. And the point is synthesis underlies all the properties, and those properties then underlie all the potential application areas, right? And this, superconductors have obvious applications in energy transport. But related materials actually have potential applications in other fundamental physics problems, like building better dark matter detectors or dark energy detections, so on and so forth.
We don't see your slides.
What?
We don't see your slides.
Let me try that again. Do you see it now?
I see your slides.
Yeah, we see them.
Oh, okay. Well,
now,
I will.
Now it's up.
Okay, I don't know what happened.
No,
okay.
it was fine. It was fine.
Okay.
No problem.
Anyways, the point is, making the materials allows you to have materials with the properties that allow you to produce phenomenology that's useful for everything from basic human knowledge to practical applications. And so, that's where we are. And so within this sort of large domain, my research is very diverse. Here I show a few examples of things that I'm not going to talk about today, just to highlight A, the diversity, and B, just some of the things that I think are kind of fun and interesting. So in the upper left here, this is a piece of a crystal of a material called samarium hexaboride, which is a topological condo insulator. What I like about this is using a technique from material science called microcomputed tomography to actually look inside this flux-grown single crystal and see if there are inclusions of the aluminum flux. And indeed, you can, and the contrast has been adjusted to highlight low Z aluminum inclusions. You can see very nicely that, in fact, there are aluminum inclusions in this. But even more importantly, you can see that they're not oriented randomly, that, in fact, they have very distinct orientations. And this makes sense because the aluminum and SMB6 have lattice parameters that are less than 1% difference. So epitaxy on each other is totally possible. But the implication of this from a physics interpretation perspective is you cannot, in your analyses, assume that any flux inclusions are randomly distributed in this case, or indeed in many other cases. In fact, oftentimes they orient in very specific crystallographic orientations relative to the underlying lattice, and therefore can still show angle-dependent behaviors, even though you might naively assume that they're randomly distributed. So I thought that was kind of fun because it was like one of the first applications of micro-CT in physics. We have lots of papers on how to make materials. So Tanya wrote this very nice review article in Chemistry of Materials on that sort of pulls back the veil on many of our tricks of how we make materials. Jen met a student, Brendan Ortiz, at one of our Paradigm summer schools. They got to talking. Brendan showed him a structure they were making for thermoelectrics. Jen said, hey, that looks like it's got a nice Kagame network in it. I bet it has interesting physics. And well, the rest is history. And so that has led to this whole field of these metallic vanadium Kagames, which show superconductivity and a variety of other interesting physics. And then here on the right, it's a similar thing where this material in the middle here, niobium 3-bromine 8, was a candidate quantum spin liquid that my group helped develop. And as sort of step 1 of 40 of trying to make an ultimate device where you might be able to actually like measure the entanglement in the quantum spin liquid directly, the step 1 was to make this Josephson junction. So NBSE2 superconductor, insulating NB3 Br8, insulating or superconducting NBSE2 makes a Josephson junction, and resulted in the discovery of this something called the field-free Josephson diode effect, which basically means there's a parameter range where supercurrent flows one way and normal current flows the other way. So it's a diode, but for supercurrent. So in order to realize all these things, there's really 2 grand challenges that my group tries to tackle. The first is how we make highly structured materials, right? So if you take inspiration from biology, bone is which is what's on the left here, is a rather remarkable material because it's very bendable, yet very strong and very hard, right? That becomes because of its tailored structure across many different length scales. And then on the right, of course, levitating supercelestars maybe isn't the most useful thing to do with a superconductor, but it demonstrates the possibilities of what you might be able to do if you could harness some of these quantum effects on a macroscopic scale. So, so I think I'm just looking at the time here. I would just say I think this entire audience here is very familiar with this idea that in the last 20 years, computations have come a long way. And this has led to our ability to combine intuition with things like ab initio DFT. This example is not my example. This is from James Rondinelli, and I like it because it's a nice example of how do you find a polar metal. And you start with sort of the fundamental symmetry considerations, use that to derive sort of specific mechanisms by which you can break symmetry and land into one of the polar crystal classes, and then actually doing DFT calculations and showing that for specific materials, in fact, these things should be stable as polar metals. And this led to the discovery of polar metals by design, right? So not just sort of randomly, but sort of in a systematic designed approach. Okay. So, if we sort of want to talk early on what was going on with sort of computation before the modern AI ML craze, the thing that was interesting to do was to say, could you use computers to actually predict which materials are stable? This, again, is not my work. It's just, it helps set the stage. So this is from Ken Poppelmeier and others, where they took this 111 family of materials and said, okay, which ones are known? That's all the black checks. Okay. Then all the ones in purples are the ones that computationally were predicted to exist. And then the ones that are check marks in purple are the ones that they went and made and found that indeed they do exist. Now, as a chemist, this isn't necessarily all that surprising because the reality is if, titanium, cobalt, arsenic exists, and titanium, rhodium, arsenic exists, then you would highly expect titanium, iridium, arsenic to also exist. So, you might say, well, what's the big deal here? This is like something any chemist can figure out, in 10 seconds. The big deal is you didn't need a chemist to know that. The big deal is the computer was just able to do that. You were able to figure it out on its own from energetic considerations. That was the big deal, right? So with that as the stage, let me now talk a little bit about superconductor design and where AI and ML sort of fits into the picture. So applying sort of these kinds of design principles to superconductors is not new. So Bernard Matthias, arguably the most prolific discoverer of superconductors ever, has a number of sort of famous papers where they elucidate some basic design rules, right? So here's one for certain class of intermetallic compounds. The number on the y-axis here, it's proportional to Tc, the critical temperature of a superconductor. And this x-axis is the number of valence electrons. And they said, hey, look, basically you want to either get just under 5 valence electrons per atom or just under, or right around 7 valence electrons per atom. And that's where you'll get high TCs. And indeed, this sort of design principle is what led to what are called the A15 superconductors. Okay. Once the high TC cuprates were discovered in 1986, 1987, people said, well, we can enumerate all possibilities. And so I don't want to spend the time to walk through this chart on the right, but just this chart on the right is essentially a very condensed representation of the enumeration of a very large number of possible mixtures of elements that might theoretically, maybe, form structures that are comparable to that of YBCO, YBCO. And there's sort of little chemical intuition in this particular plot. And indeed, none of these exist essentially for chemical reasons. But it illustrates nonetheless the idea that you can, maybe if you applied the right kind of statistical tools or the right kind of design principles, maybe you could in fact go and find new superconductors systematically. And so that sort of sets the stage for modern various attempts for applying AI.
Sorry to interrupt. I have actually a question. So in this discussion, are you going by just the statistics and trends, the common trends among different classes of materials that show superconductivity, or you're looking some theoretical framework? Because
I will get to that. I will get to that.
Okay,
I will get to that. That's a great question. And B, I will get to that.
Okay, perfect.
I guess what I would say is up to this point, right? Up to this point, this specific example was a pure statistical example, right? There wasn't sort of any, real theory of superconductivity there. But we're getting there. We're getting there. It's a great question. So, of course, at the modern stage, what about AI/ML methods? And here's where I just need to remind everyone that in this modern parlance of AI/ML, lots of things are AI/ML, even if we may have used them, 20 years before AI and ML was a hot term, right? So machine learning and AI methods are typically divided into what are called classical and modern methods. Classical methods include things like principal component analysis, right? Routinely used for many, many, many years, or various kinds of regression or decision tree approaches. Of course, those things were very common even before the modern ML craze, but they now fall under this broader umbrella. But when most people talk about machine learning methods, they're usually referring to neural network based methods, so often what's called deep learning neural networks of various kinds. So large language models, for example, are a kind of transformer model down here. And so, when I say AI or ML in this talk, if I say it very generally, it's because actually we've done it with a number of these different tools, and it doesn't really matter which one you use. And I'm happy to give you, whereas if I am very specific about which one we use, it's because it matters. Those have grown up at the same time. A large number of sort of community databases of useful information have grown up. Materials Project, AFlow, others, as well as structure prediction tools, some of which some of you on the call are probably familiar with, for doing sort of computational-based structure prediction. And so relevant specifically to superconductors was this database developed by NIMS in Japan with Hosono, called the SuperCon database, which is a database that basically lists chemical formula and TC. Okay. And using that database, they did some very early work saying, yeah, well, we can maybe just from building models from that data, we can maybe make some predictions. But now to walk through a little bit more in detail exactly where things were and then where we added to it. So I'm going to take this paper as one of sort of 5 papers that came out all right around the same time, 2018. And I'm going to pick on this one because Corey is a colleague of mine. He's in material science now here at Hopkins. Efrain and JP are longtime friends of mine. So I'm going to pick on this one a little bit just to highlight how far we've been able to come since this work. So if you look at this work, you know, the sort of the central result of this paper is to say, well, look, if we train, and just to orient everyone, these are the important kinds of plots in this field. You plot the prediction. So you are building some model that is then making predictions, and you're making predictions on what's called a withheld set of test data, so data not used to train your model. Okay, and what you do is you plot the predicted value versus the measured value. And if there were in perfect agreement, these would all fall on a straight line whose slope is 1 and intercept is 0, right? And so basically how close they get to such a straight line is used as a measure of how well is the model doing. And so for the models that were used in this work, which derive themselves from the SuperCon database, you know, you get a plot like this. Now, this plot looks okay, and in some sense it is, but notice that these are log scales. It's the log of TC. So in fact, actually, some of these things are considerable, you know, factors of 10 spread in values, right? From prediction versus reality. But to the earlier question about models, one of the fun things you can do when you have a database like this, and that this paper did very nicely, was to say, well, what if I only train on one class of superconductor? What if I now try to predict TC of a different class of superconductors? And you can see that, like, if I train on the low TCs, I don't predict the cuprates. If I train on, and I don't predict the iron compounds, if I train on the cuprates, I don't really predict the low TCs. And if I train on the cuprates, I don't predict the iron compounds. Suggesting, perhaps as we have sort of thought in the community, that maybe there are different sort of mechanisms of superconductivity here, potentially. But there's a big asterisk to that, which we're going to get to in just a second. And the asterisk is if you look at sort of the new predictions, okay, these are all existing things, but if I now take things that haven't been measured or aren't known to be superconducting or not, and you ask this model to predict which new things should be superconductors, you get this list. And this list is very bothersome for solid state chemists because cesium, beryllium, arsenate is going to be an arsenate with a little polyhedron of oxygen, and beryllium and cesium. This is probably going to be a 10 eV band gap insulator, maybe a great deep UV optic material, and assuredly never going to be able to have its electron count changed to be turned into a metal or superconductor. And indeed, that's the problem with essentially everything on this list. And so if you actually look in detail here at what these predictions look like, actually what the models learned was lots of oxygen equals high TC. Right? And of course, why is that? The SuperCon database has a lot of cuprate entries. Those cuprate entries have a lot of oxygen. They have higher TCs than anything else in the database. So it's not all that surprising, but that this statistical method says, hey, there's a correlation between oxygen, the amount of oxygen in the formula, and TC. And so this was a little, as someone who likes to make materials, this list was very disheartening because it was like, well, I'm not, most of these are not really worth the effort from the perspective of superconductivity. Okay, so now let's think through really how these tools work and how you really might use them. And again, this is all just sort of set up what my group did. So first is what funding agencies might want is this. They might want a tool where you basically enter, say, I want a TC that's at least 350 Kelvin, a high critical current, a high HC2. And this is all just so that I can build real magnets out of these things, all at 1 atmosphere of pressure with no toxic elements. And I want to somehow have a tool that then tells me, make this compound in that structure, and here's how you do it. Now, no one yet has really done this, and unsurprisingly, because this is like many hard problems all wrapped into one, right? Like, knowing how to make a material is a hard problem. Knowing what the structure of a material is given the chemical formula is a hard problem, right? So knowing whether or not a given material is a superconductor is a hard problem. So no one's done this. But all of the previous examples I just showed you were actually examples of the following sort of general logic. Is what is the TC of, or is it a superconductor, based on the chemical formula. So if I take B8.6, K.4, BiO3, can the model then tell me the TC, or whether or not it's a superconductor above some temperature? Okay. Now, this is still asking this model to solve many hard problems at once, because there are isomers, there are polymorphs. The chemical formula does not uniquely tell you the arrangement of atoms, right? And as you if you keep the same formula but change the arrangements of atoms, the properties change greatly, because how the electrons are able to spread out on that lattice changes greatly. So what my group said is, look, what if we really take this as a challenge to really only try to solve one hard problem at a time? And in particular, let's try to give as input to the model, not just the chemical formula, but the actual structure, with the hopes that then maybe we can learn a map from that chemical structural view to TC that maybe isn't just a correlation, but maybe has some causality elements to it as well. So that's what we did. And so the first challenge you have to address when doing this is, how do you represent a crystal structure in a uniform way to apply various neural network models, for example. And this problem was tackled for us by a paper that came out just as we were starting this work, which is in PRL, which is very nice, on something called a crystal graph neural network. I'm doing a gross disservice to the details, but basically what you do here is structures are atoms with neighbors. That means you can represent this as a graph. Okay? That means you can represent any structure as a graph. And once you can represent any structure as a graph, now you can decide how you're going to truncate or not truncate that graph to uniquely represent a given structure. So that part was figured out for us. The other part, which is where 90% of the work actually was we needed structural information to associate with TC values. And Supercon didn't have that, right? So through a combination of manual, automated, and semi-automated methods, my student Maggie on this assigned for every entry in Supercon, and a whole bunch more entries that we added to it as well, and I'll get to that in a minute, a information about the structure. Now, we didn't know, now for almost all of these, there isn't the detailed, like, here's the exact lattice parameter, here's the exact atomic positions in the crystal structure, but at least the structure type. And if you'll notice, that's useful if you're going to represent things as a graph, that it doesn't capture these details of like distances, but it captures very well the connectivity, right? So we added to the Supercon database all of everything that was required for understanding the connectivity. And then we do all the same games that you saw sort of in the previous work that I went through by my friends. And and so now here's a plot of measured TC versus predicted TC, now on a linear scale. And it's not bad, okay? Just like, again, this is okay. It's not bad. It's certainly better than in many areas of science, the level of agreement here. But then you'll notice there's a whole bunch of real outliers here, right? Like, look at all these, right? Those all have a predicted TC that's basically the same, but the measured TC is markedly different. These are actually not issues with the model per se. They're issues with the data that we're comparing to. Because many of these points that are these big outliers here, they are things where the chemical composition was not figured out at the time. And in hindsight, we know, for example, that oxygen content matters a very great deal for the superconductivity of yttrium, barium, copper oxide. But many of these points have essentially the same composition because it wasn't determined analytically at the time. So I feel like if you have a model where the main discrepancies between the model and your, quote, ground truth is limitations in your ground truth, then at least from a correlation perspective, the model's not doing so bad. Okay. What excited me a little bit more about this work was that if you look at the things that are predicted, so you can see that. So first of all, in terms of what materials to pull off of, many of these are large numbered entries in materials project, which means they're computationally predicted, but not experimentally made, at least not yet. And so I'm excited about this list because these, from a sort of a structure perspective, seem to match what we know are important ingredients in superconductivity, in the sense that you do need to have direct connectivity. You can't have isolated polyhedra, that you do like things that are layered to get really high TCs. Okay. Unfortunately, these are either very, very difficult to make or are very, very difficult to change the electron count of, which is what you need to actually get to an electron count that would promote superconductivity instead of some kind of ordered state. So, but I feel like this is useful for us because it says at least, hey, if you include the structure information, you start to develop these maps that actually consider the structure and produce useful things. And so that set up a project that went for 3 years with the Applied Physics Lab here at Johns Hopkins, where we said, look, all of this theory work is useful and teaches us things, but what if we really connect the experimental synthesis with the model building in sort of a very tight-knit, very closed-loop fashion? Can this then really actually do something? And so this is a very complicated story, and it's a very complicated paper, but you're welcome to go look at it. You're also welcome to go look at the SI, which has hundreds of data points that actually make in and of themselves a useful data set. The key idea here was to experimentally make materials, both that are superconducting and that are non-superconducting, and then provide the experimental data. So when I say providing the input structure, I don't mean providing crystal information. I mean providing a powder X-ray diffraction pattern, right? So to provide information that's sort of directly from the experiment, in some sense, okay, as input to model training. Use that to make new predictions, which we then go and try to make, and then we feed all that data back in and try to improve the model, and we go around this loop many, many, many times. So it's a combination of human and machine that together are working together to iterate very fast. And so what we did in round 1 was to make a bunch of known superconductors and known not superconductors. You might say, well, why didn't we pull this from the literature? Well, because actually it was faster for us to just go and remake things. But more importantly, when you don't have a large amount of data, and none of these problems are large data in the context of AI/ML, when you don't have a large amount of data, you can very easily pick up on spurious correlations due to various kinds of systematics. And you can avoid a lot of that by making sure you have made and measured all samples on the same systems. So there's a whole bunch of systematic errors there, but they're the same across all of them. And so we don't have to, and so the model doesn't pick up on them because it's the same across both the superconductors and the non-superconductors. Okay. So we made a whole bunch of like A15s, for example, which are mostly what's shown here. Then you use that, and we were indeed able to predict some things that were not anywhere in the training set, but are known to be superconductors. We were then able to find this zirconium nickel indium compound, which is actually hideously hard to stabilize, and I'll come to that in a moment. But that was a truly new superconductor. And so I start to get really excited with this because it's like when we're, you can ask about the frequency, okay, and we'll get to that in a second, but like, what fraction of the predictions were successful here? And it was, 3 to 5 times what my former PhD advisor was doing in terms of, number of samples that end up being superconducting, number of new materials. So it's, which is to say, compared to a human expert, actually pretty good at generating leads that lead to superconductivity. And I am really excited to see where this field is going because in the this is sort of field is now growing very rapidly. So there's some nice work from folks at University of Florida, right, where you actually add physics in the model. So for example, you train, phonon density of states, you train Elijah-Berg spectral functions, and then use that to, in fact, decide on different substitutional combinations, which then should result in various superconducting TCs, and then in fact realize them in reality, such as was done in this very nice work. I saw Professor Hoffman join the call. I think this idea of treating solids as molecular units has been incredibly beneficial. You can take that a step further and really just start from sort of first principles. If I just write down, we know how to write down single particle, expressions for things on extended lattices through tight binding models. If you then say, well, let me add a hypothetical pairing interaction of some general form to result in the formation of Cooper pairs, what really changes, and what are really the key ingredients in the structural aspects of this that allow for this to happen. And I apologize, I should have taken out the check out Greg's poster this evening. But you can check out this work on the archive, where we start with a crystal field perspective of how orbitals behave on lattices, inspired by Roald Hoffman, and then take that a step further and say what arrangements, what patterns of that result in more or less ability for the electrons to pair and form actual superconducting wave functions, which is what's plotted in the bottom left here. And this actually has resulted in some useful insight for us, and this is very fresh work. So we're actively in the process of exploring materials based on this design principle, both generated by humans and generated by machine. Okay, so that was a lot very quickly. But one question that you should have been asking at this point is, would these tools have actually accelerated discovery? Because the reality is, at the end of the day, if you think about, humans do a very good job of optimizing systems. Humans do a very good job of very efficiently exploring spaces. So would all of these kinds of things really have accelerated discoveries? And so to answer that question, I worked with my collaborators at APL to come up with a thought experiment, so to speak, that we could run based on all this data and actually ask ourselves, how long would it have taken, if all we knew was the low TC intermetallics, how long would it have taken to find new families of superconductors? Okay. And this plot is the important plot. So this axis here is the batch number. That's basically the number of cycles going around that sort of loop that I talked about earlier. And this is cumulative number of discoveries. These all have error bars because we run the simulation many, many, many times to get averages and error bars. And these are with different sort of sampling strategies. So in terms of, you have a model, that model is then predicting new compounds, but how do you, of the things the model predicts, how do you sample the ones to go after? And sort of greedy is like, select the ones where it predicts the highest TCs. Epsilon tail is, I don't want to describe that right now. But then like uniform is like, well, you just select them, quote, randomly. Okay. And so what happens here is that indeed the greedy approach is able to much more rapidly find new families. Oh, the table would help. New families of superconductors, in terms of, sort of this is essentially, if you hold out the cuprates, for example, it only then these various sampling algorithms are able to find the cuprates in relatively short order using models built from the experimental data only on the low TC compounds, plus the new data you feed it when you run its top results. And so the answer appears to be yes, these will accelerate discovery, but they're not going to be a panacea. They don't instantly make the process of discovery go to, well, plug it into the computer and it tells you the answer and you're done. No, You still need this very closed loop process, but there are useful correlations that these models pick up on that are not obvious to humans, and those indeed allow you to find new families of superconductors. So that leads to some of my personal observations that many of these methods are not black magic, but they're also not a panacea. Microscopic models are helpful because they can help avoid spurious correlations when you're building these models, but they're not required, right? And in fact, what seems to be most required is to have really, and this should surprise no one, okay? But what's actually most important is to have really high quality input data for what you're training your model on. This isn't a problem space where there are essentially infinite number of inputs, and therefore you don't have to worry about the reliability of any one input. This problem space is the opposite problem space, where you really, all of those things that make good for good science, make for good AI model building too. Unfortunately, despite these sort of theoretical examples saying, well, it would have accelerated discovery, these methods haven't really actually moved the needle in preparing the predicted materials. And so this has led, in my opinion, to this unbounded growth of a large number of materials predictions that have no hope of existing in reality. Okay. And so I think it's really important that we find ways to encourage unbiased and impartial assessments of results, both theoretically predicted and the experimental results, in a much more unbiased way. Because there are lots of papers that claim these problems are solved. So a very simple example of a place. So there are many papers that claim the process of predicting phase diagrams is a solved problem. And then there are many experimental solid-state chemists who try to use those phase diagrams to predict things, and they don't predict the right things. But when they do predict the right thing, you always get a nice paper out of it that says, hey, look, and the theory predicted this, and we made it, and oh, look at how well it did, while missing the larger picture. How well are they actually working or not working? And so I think it's really important for us to think about how to do this in a much more unbiased or impartial way. And I think it's also important for us to think about, as we automate more and more of our tooling, how do we retain the ability to have that unexpected discovery because someone was observing the color and said, hey, wow, that turned black, or, oh, that material was supposed to be yellow and it's actually green. I wonder why, right? And of course, those are like those are the kinds of observations that then lead to real discoveries. And so just in the interest of time here, I think I'm going to skip some of that. And basically, I just want to talk about this how to make it question. So, I get asked all the time how these methods can help with how to make. And so the obvious thing to do is to use your favorite large language model or a train or a modified version thereof. And you can say, well, ask it how to make something and see how it does. And so to really test where these do and don't work, my group did this A/B, synthesizability study. And hopefully we'll see a paper on the archive in the not too distant future. This is enabled by my student, Greg, and Wyatt, and a whole cadre of undergraduates who helped provide the power to make this happen. And so the idea was, let's pick a single family of materials, which are Ruddleston poppers. Okay, so they're layers of rock salt and perovskite. And the advantage of this is that we can generate many members of these series that are known to exist, many members of these series that are known not to exist, and many members of these series that aren't known to exist, but they should exist. And then what we did is, starting from those, we then said, okay, suppose I want to make SM3CO2O7. Let me send it to a human, which is Greg and I, to write down a synthesis procedure. Here's how we would make it. We then provided this to an APL version of ChatGPT, which is basically ChatGPT, but it has tools it can call out to that can help inform its decision-making process. Okay, and have it write down a procedure for how to make things. And then we have two different people, one who's sort of an expert in synthesis, try both syntheses, and one who's a novice in synthesis, try both syntheses, get the results, and if they're successful, we're done. And if they're unsuccessful, we pass them back around. We pass that information back to both the human expert and the LLM model and say, well, that didn't work. Here's what actually happened. What's the next thing to try? Okay. And so this whole experimental design actually lets us learn a lot of things at once. But the only part that I want to tell you about today is how does this actually do? Well, in 40% of cases, both the experts and the LLM methods that are written down actually work for making the material. Okay. There are 9% of cases where the human written procedures worked and the LLM generated procedures failed. There are also, interestingly, a small percent of cases where the human expert failed and the LLM succeeded. If you look in detail at where they succeeded and where they failed, here's what you learn. The places where the human succeeded and the LLM failed, these are universally in cases where there was some creativity in how the synthesis was done, like some clever idea for how to use a flux that wouldn't be the normal flux, or some clever insight into how different things may react, and thus maybe making it a two-step synthesis process instead of a one-step process. Those were the places where the human expert succeeded and the LLM failed. And the cases where the LLM succeeded and the human expert failed, in every cases, this was a case where what I'm going to call a global average synthesis works, and the human thought it couldn't possibly work, and therefore designed something more complicated that then ended up not working. So one thing all of these AI tools tend to do is when you provide an input where there's really nothing comparable in the training data, they oftentimes tend to revert to an average. Okay, so if you somehow take all solid state synthetic methods reported in all papers and construct some sort of global average, that's, what does that mean? Heat to 1000 C in air overnight to a first approximation, right? And so when there really is nothing in the training data that is matched by the model to be similar to what's being asked, it just returns this sort of global average, right? Because it's all about probabilities, okay? And the cases where the LLM worked was when that actually works. And the human thought there was a reason that wasn't going to work and therefore decided to write something more complicated instead. Okay, and so I think this is really the gap. Synthesis in theory versus synthesis in practice. That, synthesis in theory, we can do lots of thermodynamic calculations, right? So we know how to compute, as a function of chemical potentials of, in this case, it's tantalum and nitrogen, right? For tantalum nitrides, we know how to compute as a function of the chemical potential of those elements, what different phases will be stable. We know how to compute convex hole diagrams. But here's a control panel, for a typical, MBE, for example. Well, this is an MBE specifically, but typical synthesis tool. I don't see any knobs labeled chemical potential, right? I also don't see, it's also not just a single step. It's like many steps, right? Again and again and again and again, right? Also, like, for the convex hull, I need to know the temperature. Yeah, but how do I really read the temperature? And where are, the reality is temperature gradients become important, right? Or in other cases, here's a pure solid state one. It's not a single step, right? It's, okay, first I have to clean up my starting reagents. This is to make a inflate layer nickelate, which is in thin film superconducting. You got to clean up your reagents to begin with. You then have to, make the material, and you need high pressure oxygen to do it. And then you have to remove the oxygen, and to do that, you sort of, need this two-step process or one-step process, depending on how you do it. But the point is, it's now a low-step process. This is a multi-step synthesis where it's not a constant set of thermodynamic conditions. You're not just at thermodynamic equilibrium. You are very much relying on the ability to change the thermodynamic variables as a function of time. And I think right now, from a theory perspective, that is very poorly captured, right? So, or said another way, the reality is real syntheses for most real materials today, they're not set the thermodynamic parameters at some value and leave it, and they're not just continuously change them all sort of uniformly. It's much more complicated. It's changed, 3 different thermodynamic constraints, maybe, composition, temperature, pressure are the obvious ones, but there are many others as well. Electrochemical potential, for example. And you control those as a function of time in a very controlled way to make things, right? And this, combined with the fact that there are often systematic errors and gradients and all these kinds of things, make this very, very hard to treat using current methods. But that's all the more reason to try to tackle this problem, because this is, in fact, a very hard problem. And we are now at the point where, combining Google's DeepMind's work, Microsoft's generative AI work, we do some work with Microsoft, and some of the superconducting models that I showed you earlier, we can generate, thousands per day of candidate new superconductors, and for the most part, no idea how to make them, right? No information on how. Right? So that's where the challenge is. And so maybe I'll just end on a high note with respect to synthesis, which is, control of synthesis goes far beyond just setting thermodynamic conditions and leaving it. So here's a canonical example. This is happening in all your cell phones, in the batteries today. So lithium cobalt oxide is a layered crystal structure with lithium, and you can pull the lithium out. Now, how might I do this? Well, there's lots of ways to do this. One is to literally build a battery, build an electrical chemical cell and provide a voltage, right? That's one way to move the electrons in and out of this material. Another way to do it is to use a chemical oxidant. So if you start with LiCOO2 and you mix it and you suspend it either as a crystal or as a powder, you suspend it in a solvent, acetonitrile, with an oxidant like iodine or bromine, and then you wait sufficient time for that oxidant to actually oxidize the lithium cobalt oxide. You can also pull the lithium out, right? You can also go in reverse. So if you start with like Li.3COO2, you can take it, suspended again in a solvent, usually a solvent called THF, tetrahydrofuran, and you can add this reagent called butyllithium. It's a fun reagent to work with. It catches fire in air. But the point is it's a strong reducing agent with lithium, and you can then literally insert lithium and go the other way. And this is all known. This is all, well worked out chemistry. With respect to superconductors and the nickelates, right? So here's a transformation that you want to do in that field, which is to go from the perovskite LaNiO3 to this layered, so-called infinite layer, but it's just layered oxygen-deficient perovskite, from LaNiO3 to LaNiO2. And there was work that was done about 25 years ago that pioneered a very clever way to do this, which is to basically use a hydrogen-containing reducing agent, calcium hydride or sodium hydride, and very carefully controlling the temperature, going to 280 Celsius. And if you went 5C hotter than that, you decomposed the material, and if you went 5C lower than that, you didn't get a complete reaction. Okay, but there was a lot of question in the nickelates: does hydrogen matter for the superconductivity? You'd love to be able to do this kind of reduction without any hydrogen around at all. Turns out that's shockingly hard to do, because basically almost all reducing agents contain hydrogen. So, but it turns out, if you think back, there's this thing called an amalgam. So an amalgam is from 150 years ago, is like sodium metal dissolved in mercury metal. And I don't really like my students playing with mercury, so you can come up with an aluminum gallium eutectic that serves the same purpose as the mercury, which is to say a liquid. And then you can add the alkali metal, sodium or potassium, as the reducing agent. And it works. And I guess I'm running out of time, so I think I'll just say it works. And the cool thing here is when you change the concentration of the alkali metal in the gallium aluminum eutectic, you change the electrochemical potential. So rather than just sitting at a fixed electrochemical potential like with CaH2, By changing the concentration of the alkali in this, we can change the electrochemical potential. And what that means is that we no longer have to be quite as perfect in our temperature and timing, because we can continuously vary that electrochemical potential to a place where the reaction occurs, but we're not going to get over-oxidation. And so we're able to very controllably take LaNiO3 to the so-called brown millerite, LaNiO 2.5, and then also differently systematically to LaNiO2. And so this is just an example of a sort of a new chemical development inspired by a physics question that illustrates, sort of the frontier in complexity in material synthesis. And I think with that, I will happily take any other questions. And thank you for your time and attention.
Thank you, Terrell, for a great talk. Wonderful. The seminar is now open for questions and comments, additional ones. Just unmute yourself, put the comment or question in the chat, or raise your hand. Maybe I'll start with going back to the predictions of TC and following the Nicolates here. You focused on structure, existence of polyhedra, maybe orbital tiling, and so on. But at some point, lattice parameters also matter. So coming at this from the standpoint of pressure. So could the Nicolate superconductors been predicted by AI with these tools? And also at what pressure? With what lattice parameters?
No, that's a great question. That's a great question. So the way the lattice, for the models we've built, the way we incorporate the lattice parameters is as a total cell volume. Or it's really a volume per atom is what it really is really the thing that we input. And that's a very imprecise and indirect thing. I have no doubt. So I gave this crystal graph neural network, which is one way to represent a crystal structure. I have no doubt that if we used one of the other methods that we have available now, which in fact capture the details of the bonding geometry, I have no doubt that those actually would do a very good job of making these predictions. The challenge there will be knowing what to expect that geometry to look like as a function of pressure, for example.
Right. Christoph, go ahead. Christoph, do you have a question?
Sorry. Thank you very much for this beautiful lecture. Although I do not agree with this polyhedral representation of structure. You do not have polyhedra in crystals. You have nuclei and electron density. Why not to feed all these artificial intelligence programs with details of electron density? For me, there is no doubt that superconductivity is related to, say, valence electron density. And that's one thing. Second question is, in your opinion, is superconductivity isotropic property or anisotropic?
Okay, so I'll answer the first question first. So yes, absolutely, electron density is almost assuredly a great thing to feed in. And I kind of alluded to that when I said in our experimental closed loop, what were we providing as the structure? We were actually providing X-ray diffraction patterns. And X-ray diffraction patterns are really just experimental measures of electron density, right? That's what they really are.
Yeah, but let me interrupt at this moment, because those patterns you were showing, these were only low-angle patterns representing Bragg diffraction only. The point is that you've got structural information in between the Bragg peaks, and this information is about deviations from this ideal symmetry. And in fact, all the systems, when you take a look at the local structures, they are not that beautifully symmetric. They can deviate from symmetry very much. But you simply do not account for this because you do not use high Qs, do not use high resolution data.
Well, okay, let me be clear, right? So what I showed in my talk here was, especially in the AI ML part, was the schematics, right? So the technical detail there is the routine thing we used was what we had access to in our lab at a time, which is copper 2 theta powder diffraction from 5 to 120 degrees. But a totally different slice of my life is actually looking at all of these deviations from the average structure using the information between the Bragg peaks using techniques like pair distribution function analysis.
Yeah.
And there's a bismuth oxygen sulfur superconductor that I can point you to, where indeed, if you train the model just on computationally predicted diffraction patterns, it doesn't do a good job of predicting things. But if you feed it the actual powder diffraction patterns, it does do a good job of predicting things. And if you tease out why, it's precisely because it has to do with not specific material. It has to do with the different kinds of layering that you get, and the information on the number of those stacking faults and things is sort of encoded in the peak shape. So I don't disagree with you at all, and agree that this is exactly the kind of thing that that should be done next in this kind of area in a more formal way. I 100% agree.
How about isotropic or anisotropic character of superconductor?
Well, there's a compound we just published a paper on, LACUSB2, which behaves as a type 1 superconductor in one crystal direction and a type 2 superconductor in a different crystal direction. And I would argue that you might in a mathematical sense still call it isotropic, but it's not. But clearly that's a high degree of anisotropy in the behavior.
Mm-hmm. Mm-hmm. I also think that simply reciprocal lattice information up to the very high resolution could be also very good to be used in all these prediction programs. Thank you very much.
I agree 100%, and we have a silver X-ray diffractometer that is letting us get higher angle data to higher Q with reasonably good resolution. I absolutely agree 100%. I think Daniel had a question, and then Francesco, I think.
Yes. Thank you very much.
Yeah, thanks, Daniel. That was a great talk. So you're training these models on every known superconductor, but there are many more materials that are not superconductor.
Yes.
And I wonder if are you using the millions of materials that are not to also train the model?
So I alluded to that. So the problem in the literature is it's actually very difficult in the literature to find examples where people say it's not a superconductor. So you have to sort of infer it from the data that's provided, right? Like, oh, it's a semiconductor or whatever. So this is where we decided it was too much effort to deal with that, and instead we would just experimentally make a whole bunch of these compounds, including a bunch of non-superconductors. And indeed, it is actually really important to include the non-superconductors to help avoid picking up on spurious correlations, like the lots of oxygen equals a superconductor example that I gave, right? So yes, absolutely, including the non-superconductors is very important, and it's just that's easier to do for us by just making a whole bunch of them.
I see. So in terms of distribution of electrons, you're talking about electron occupancies, but how about how electrons are distributed within an atoms, within, say, between T2G and EG orbitals, high spin, low spin? Is any of that? The model doesn't know anything about this.
Well, it depends on which model we're talking about. So the closed loop thing I was talking about, you're right. The model knows none of that. It just knows sort of a snapshot of the overall electron density. Some of these, what I called physics informed models, are starting to include more of that information that you just described.
Thank you.
Thanks very much, Francesco.
Hello, Tyler. Can you
I hear you great. I hear you great.
Perfect. Yes. Very nice talk as always. And I had a question when you, for instance, show the ability of your model to predict DC, because you have included many different classes of superconductors, and I wonder what is the mechanism of all the system. Do they all have the same, or is the model able to predict?
That's an excellent question. So first of all, I encourage you to go read. I can't find it here. I encourage you to go read this paper, because I didn't include it in the talk, but we did many of these same things of training models on subsets and seeing what they could and couldn't do. And I would say it was actually better than the previous results. So what I infer that to mean is structure actually carries a lot of useful information about whether or not something's superconducting. Now that I've said that, this work here, I would argue on the basis of this work here that the mechanism in the sense of what's providing the pairing energy could be distinct among the different classes of superconductors. But the fundamental sort of structural ingredients, and by structural I mean sort of, where the electrons are and where the nuclei are, the fundamental structural ingredients you need to induce superconductivity is more universal. Now,
yes, fair enough. Okay. Yeah, that is exactly what I wanted to get to, because effectively there has to be something that pairs the electron, but effectively there has to be some electronic property that is there to be paired. So yeah. Right. Yeah, thank you very much. This is actually very useful.
Yeah. Thank you. More questions, comments? Okay, well, if not, thank you very much, Terrell, for a terrific talk.
And again, thank you for the invitation. And you all know how to reach me, so feel free to reach out if you ever like to chat about anything.
Yes, and we continue to need samples, so we'll be in touch.
Okay, all right, sounds good.
Okay,
take care.
Thank you, everybody.
Thanks.